The essay begins here. Introduction. Thomas Young's 1800 unpublished paper on the theory of light and colours represents a pivotal juncture in the scientific understanding of optics. This work, presented before the Royal Society and subsequently published in Philosophical Transactions, offered a compelling alternative to Newtonian corpuscular theory, proposing a wave model of light. This essay undertakes a detailed, section-by-section examination of Young's paper, scrutinising its arguments, methodologies, and the evidence offered in support of its claims. The objective is not to provide a general overview, but to critically evaluate the internal coherence and validity of Young's assertions, highlighting their contributions and their challenges in the scientific landscape of the time. The evaluation focuses on the intricate specifics of Young's propositions, assessing their theoretical foundations, experimental support, and the implications they carry for the understanding of light, colour perception, and the scientific methodologies employ. Section 1, Introduction and Initial Proposition. Young begins his treatise by outlining the perceived difficulty of the prevailing theories of light. The Newtonian corpuscular theory, while extremely influential, encountered challenges when attempting to explain diverse phenomena, particularly those related to the observation of colours. The section asserts an alternative light's qualities are derived from the characteristics of undulations, akin to those that propagate through a fluid. His primary claim is that the sensation of different colours arises from the varying lengths of these light waves. Young introduces the principle, then novel, that the colours of the spectrum are generated by waves of different frequencies. This is a fundamental assertion, the basis for the subsequent development of his theory. A critical assessment of this initial proposition requires acknowledging its radical nature in 1801. The wave model, though present in prior scientific thought, had not been developed with a precision or afforded the explanatory power that Young would give it. The initial claim's appeal stems from its potential to unify seemingly disparate observations under a coherent framework, a defining characteristic of successful scientific theory. Section 2. The principle of interference and its demonstration. In the following sections, Young introduces the principle of interference. Young asserts that light waves, under certain conditions, can interact, either reinforcing or cancelling each other out. This interaction, a core element of his argument, is demonstrated through the famed double-slit experiment. The details of this experiment, described with typical precision and clarity, form the cornerstone of the paper's empirical support. He describes a source of light, a thin opaque screen with two small slits, and a receiving surface. The key observation is the production of a pattern of alternating bright and dark bands, or fringes, on the receiving surface, a result unexplained by the prevailing Newtonian corpuscular theory. Young explains that the bright bands arise from the constructive interference of light waves, where crests meet crests and troughs meet troughs, reinforcing each other to produce an intensified effect. The dark bands, conversely, is the product of destructive interference, where the crests of one wave would meet the troughs of another. The significance of this section lies in the experimental demonstration of a principle that directly contradicts many aspects of the corpuscular model. Young's argument relies on the assumption that light, like water waves, could spread and thus interact, producing the observed diffraction pattern. The methodology, clear in its exposition, is both simple and compelling, providing verifiable evidence that would, decades later, become a touchstone of modern optics. The logic is, in principle, straightforward. The observed interference pattern directly challenges the supposition that light consists of independent particles. Section 3, Analysis of colours and wave length. Having established the wave nature of light and the principle of interference, Young directly applies these to the explanation of colour. He argues that different colours correspond to waves of different lengths. He uses the word lengths here, rather than what he termed frequencies earlier. Young suggests, for example, that the red light exhibits the lowest frequency and the violet light has the highest. He provides estimates, Relating the dimensions of the interference fringes to the calculated wavelengths of different colours, he uses the term wavelength to refer to the distance between crests, a term which is, even today, in common usage. To further support his argument, Young describes the observation of colours in thin films, such as soap bubbles. He explains the coloured bands seen in these films as the result of the interference of light waves reflecting from the top and bottom surfaces of the film. The different colours observed are the outcome of differences in the film's thickness, producing constructive interference for certain wavelengths, while causing destructive interference for others. The argument is advanced by the experimental evidence. The precise correlation between the thickness of the film and the colour of the reflected light. The argument's strength lies in its potential to unify observations which would be difficult to reconcile with the particle model. The explanation provides a framework by which the varied visual experience of colour can be understood. The section is a clear demonstration of Young's ability to bring the mathematics and physics of light into alignment with observational reality. Section 4: Implications and comparisons with other observations. Young connects his theory of light and colour to observations that are difficult to explain through the corpuscular model. These observations include phenomena such as the colours produced by diffraction, the bending of light around objects. Young explains that the diffraction patterns arise because of interference among light waves that spread and diffract around the edges of an object. He uses geometry to demonstrate how the angles of the light rays can be used to calculate the wavelength. He also relates his theory to the phenomenon of the colours seen in a prism, although, in this case, his explanation is less detailed than in the previous sections. He compares his explanation with those of Newton, particularly regarding the mixing of colours. He notes that the superposition of beams of light will produce bright and dark bands, resulting from interference. This comparison serves to challenge the Newtonian view of colour, which posits that white light can be resolved into the colours. The section's significance is in its extension of the theory to incorporate a broader range of optical phenomena. The detailed explanation is supported by precise demonstrations and an effective use of mathematics. Section 5: The perception of colour in the eye. Young turns attention to the human perception of colour. He introduces the idea that the eye contains 3 different types of receptors, each sensitive to different wavelengths of light. This is an early form of trichromatic theory, a seminal notion in the development of colour science. Each set of receptors, when stimulated by light, generates a sensation. The sensation of colour results from the combination and relative stimulation of these 3 types of receptors. Young does not specify the precise nature of these receptors. He posits that any colour can be created by a combination of 3 primary colours. This section brings together physics and physiology, the description of the trichromatic vision, and provides insights into how the eye may work to perceive colour. The argument is based on the analysis of colour mixing, in which any colour can be created using 3 different primary colours. An understanding of the physiology as it relates to the colour process provides a profound new way of conceptualizing the process. The implication of this theory is that colour perception is a process involving the brain more than it involves the physics of the light itself. This bold position in the history of visual sensation paved the way for future scientific inquiry. Section 6: Further demonstrations and experiments. In the final section, Young presents the results of additional experiments designed to further support his theory and address potential objections. Young provides a detailed account of how he created the interference patterns using different types of light sources and different configurations of slits. He reiterates his support for the wave theory. Young demonstrates the wave nature of light, and in doing so, provides a counterpoint to the corpuscular theory of light. He provides evidence against the particulate nature of light. Young discusses the implications of his research. He examines the implications of his theory for the treatment of light, for his analysis of many other complex behaviours of light. Further, He demonstrates why his theory can effectively explain the behavior of light in ways that particle theory simply cannot. He stresses the importance of experimental observation and mathematical modeling. The focus on experimental design gives credence to the theory. This emphasis on rigor provides a robust case for the wave theory. Conclusion: Young's On the Theory of Light and Colors represents a foundational contribution to the scientific understanding of optics. The essay, through its careful detailing of experiments and its rigorous theoretical framework, provides a compelling alternative to the dominant corpuscular theory. The paper's detailed analysis of interference, particularly through the double-slit experiment, provides concrete evidence for the wave nature of light. The work's contribution resides not simply in its core concepts, but in the manner in which these concepts are presented. Young's ability to combine mathematical precision, experimental design, and clear conceptual explanations is apparent throughout. The theory presented, while challenging the established Newtonian understanding of light, provided a framework to account for a series of previously unexplained phenomena. Young's work is a testament to the power of scientific reasoning. The introduction of the trichromatic theory of color vision provides a crucial link between the physical properties of light and the physiological processes of perception. The wave theory of light offered a paradigm shift. His emphasis on experimentation, coupled with mathematical modeling, exemplifies the scientific method. Many of Young's assertions have stood the test of time, and his work is recognized as a turning point in understanding the nature of light and color perception. The importance of his contribution continues to influence modern physics and the study of vision. Young's paper is an outstanding legacy,